we can make a real-life tricorder, so a real-life microwave scanner that can scan buildings, find leaks in pipes without being invasive, scan the ground and find cracks in the Tyne Bridge so we don't have to close it for 4 years. All of this preventative issues, which can be made with a real-life tricorder, and we are really making it, and I'm doing it right now. As long as I can remember, I've always wanted to be a gangster. Well, that's the opening line to the 1990s classic Goodfellas by Martin Scorsese. But for me, it needs one small change. As long as I can remember, I always wanted to be a scientist. I didn't know what kind, and I didn't know what I'd discover. I just knew I wanted to discover something new, something that hadn't quite been worked out yet. So, my name is Sophia, and I was born and raised in Somerset, England. But my school growing up was falling apart. Ofsted came in my most critical years, and everything felt really uncertain. But to me, the physics department really stood out. My teachers taught more than just formulas. They made me feel like I could belong in the lab. And I was the only woman in my physics class. No one had ever achieved an A-star in our school's history. So that really sat heavy on my shoulders. I felt like I had to be the one to achieve it. In my mock, I did really well, but unfortunately, that didn't translate into my A-level results day. And it made me very sad, and it made me realize that opportunity is so fragile, and one grade or one's perspective can shape a future. But luckily, I got into Northumbria University, and that pressure turned into motivation. I saw a PhD title, Room Temperature Maser. I didn't really know what a maser was, and I certainly hadn't studied it in detail. Masers are seen as quite niche, used in atomic clocks as frequency standards, but far from being widely adopted. So I took it upon myself. Can I take this signal and make it powerful? Could I take a maser out of the lab and into the public's hands? That was the quest of my PhD, and that was what I set out to answer. So, I'd like you all to imagine a world without lasers. No DVDs, no internet, no fiber optic cables, no scanning groceries, and most importantly, no lightsabers. Lasers are amazing, and they shape our everyday lives, and you might not even realize. But yes, the maser didn't have the same journey. The laser actually came from the maser. So, what is a maser? A maser stands for microwave amplification by stimulated emission of radiation. A maser does exactly what a laser does, using microwaves instead of light. So, like the lights in this room, they allow inversion. They bounce off all the walls in the room before they hit our eyes and we perceive light. Then, a laser is a cumulated, coherent beam of light. Similarly, if you have a microwave oven, microwaves bounce back and forth in your microwave oven and they heat up your food. But masers are coherent, collimated beams of microwaves. Okay? They were made in the 1950s, the first quantum amplifier. They were amazing, but they had really harsh parameters, and they just weren't able to be commercial. The laser, however, they were much more forgiving. They were room temperature, and they had much simpler materials. So while the maser stayed frozen in the lab, the lasers lit up the world. Because of the maser and the technology, and it was stale and stagnate, scientists thought at the time, what can we do with this? Can we optimize this anymore? And instead of using microwaves, they made the first optical maser. That was the laser. So, early masers were incredible, but like I said, they required cryogenic conditions that's colder than deep space, magnetic fields, and vacuum chambers. Lasers went on to win Nobel Prizes in optics for eye surgery, in chemistry for manipulating atoms, and so much more. But then, the first room temperature maser was made in 2012. It was amazing. No cryogenics, no magnetic fields, no vacuum chambers. It was amazing, but it just reached the amazing threshold. So that really sped up momentum, and I'm so grateful to say that I've worked with this team since. It motivated us in the north to make the room temperature maser, but we didn't want to just copy what had been done before. We wanted to go one step further. So we made the most powerful maser to date. How did we do that? We used new samples of active medium, that's the gain medium in the laser or the maser, called pentacene, specifically diazepentacene. We did new concentrations, 0.1%, 0.05%. We did this over and over and over again until we found the sweet spot where population inversion would sustain mazing without introducing thermal quenching. Not every day in the lab was smooth. Sometimes the cavity didn't align. Sometimes the optics were too hot. And I might have had a few electric shocks along the way. But everything came together, and we made the most powerful room temperature maser to date. We were able to ask an entirely new question of what masers can do. Instead of being a quantum amplifier, could there be something more? So, this is what a maser looks like. This isn't noise. This is a quantum wave amplified cleanly without noise. What do I mean by quantum here? It means that this wave is governed by the rules of quantum physics, which means that this maser can detect teeny tiny changes in the environment. So it can be used in quantum sensing, quantum communications, and much, much more. Maybe even quantum computing one day. What do I mean by coherence? Coherence means stability. It means the wave does not change over space and time. So together, this maser is quantum sensitive, and it's coherent. That is what a maser is, and that's why it's so impressive. Let me show you something. I don't know if you can see, but lasers are amazing. But they scatter. There you go, you can see. They scatter. They scatter through water, rain, fog, leaves. So imagine trying to send an optical signal where there's atmospheric conditions in the way. We live in Newcastle, and the cloud cover is high, so there's no optical links here. So you're very limited to where you can send these optical links. Masers do not have this issue. Masers can go through all of these conditions. Why? That's because of the electromagnetic spectrum. So, on the left, we have the high energy stuff. We have the X-rays, the gamma rays, all blocked by the atmosphere. Then we have the small gap of visible light, the rainbow that we see every day. This is where lasers are made from. And then over here, in the radio waves, the microwaves, this is where I work, in L-band. That's 1 to 2 gigahertz. And you can see there's a direct line straight to space. There's no issue with microwaves going through water, leaves, dust, smog. So this could be the future of environmental communications where optical lasers just don't paramount. So we could use masers in scanning on cars, self-driving cars, through fog where they can't see in front of them, or in disaster zones where optical communication just can't cope. We use microwaves every day anyway, but they're noisy, they're broadband. They interfere with each other, and the more and more instruments that we use with radio waves is causing a really big issue. But these microwaves, these masers, they're coherent beams, they're narrowband, They don't amplify noise. It's amazing. So, what we're building isn't a component, it's a platform. It's a new, highly secure platform for quantum communications that don't issue with the atmosphere. One step further, where else could we take this? We could take this for biological sensing, environmental scanning through the forest floors, measuring the water content in the Sahara Desert, in Antarctica, and measuring global warming over time without issue. So, in a small lab 1 mile from here, we made the most powerful maser in the world with our team, and I'm so very proud. With no cryogenics, no issue, and all I can say is, masers aren't a relic of the past, they're a product of the future, and I'm so very excited. What I spoke about today is going to be published very soon. If the story of the maser were told as a fairy tale, it would be Cinderella, because lasers go to all of the A-list parties, masers are the relic of the past. Like masers, I nearly missed my shot in science too, but together, we're finally ready and we're being heard, not with noise, but coherence. Thank you very much.
Couple questions.
Thank you, Herb.
First off, thank you very much. And I guess one question is, I mean, until Rob said the word maser, I had never heard of a maser before. And I guess why has it been so buried, in terms of, I mean, obviously we've heard about nuclear fusion, even though fusion is constantly 30 years away from us. What gives with the maser?
So, what's the deal? Like I said, lasers, they were just so much simpler. They were room temperature. They were much more commercially viable. They didn't require cryogenics or vacuum conditions or big magnets. So that made them much cheaper, much smaller. And so when it comes to science, when money is a real issue, the lasers just took off exponentially.
Okay.
Masers were great, and they're used in atomic clocks as frequency standards and GPS. But that's the people that have millions of pounds and would spend it on a couple masers.
Sure.
But these days, when the room temperature maser happened, no cryogenics, no vacuum conditions, room temperature and real.
Okay.
That was a real achievement. And so since 2012, momentum has just gained exponentially for the maser. So, yes.
Okay, so the whole thing about this, the cooling, because it's, you were mentioning it's basically near absolute zero, colder than deep space.
Colder than deep space, yes.
So how do we go from, that to room temperature? Or what was the enabling thing that happened?
Yes, so there's a gain medium in the maser. Just like a laser, you have an optical pump, an organic media, and a cavity. And this gain media was doped in a special way, which meant it didn't need magnet or cryogenics to make that maser happen.
Right.
So very specific organic chemistry allowed for that maser to happen, as well as different shapes of microwave cavities that encapsulate the maser crystal.
Okay.
A whole bunch of things all together made that room temperature maser.
Okay. So, I mean, I realize it's a really early stage, but would you say it's a high likelihood that masers will replace lasers in all sorts of applications?
So many, but at the same time, we would want to work alongside lasers. We wouldn't want to replace lasers in all cases, because at the end of the day, the more of the electromagnetic spectrum that you can communicate with side by side in a coherent wave, the better.
Okay.
Instead of Lambertian waves, we need as many coherent beams as possible that don't interfere with each other.
Okay.
And light and microwaves, they can run side by side without any interference. So yes, we would want lasers and masers to work together.
Okay.
But where masers would step maybe once in front of the laser is the issues with atmospheric conditions or leaves, etc., because microwaves can pass straight through and lasers just can't.
Okay. Although probably in your future investor pitches, you will probably not talk so much about how we're all going to get along, But where's the maser likely to dominate the laser? If you were trying to apply it today,
Yes.
as I'm sure you're going to be doing in the near
Yes.
future, where's the first place you're going to see the maser in real life?
Other than communications,
Well, no, within communication.
Within
So, like, what's
communications?
because I think
Yes.
is communications your most likely
I would say
use case?
communications is our most likely use case.
Okay.
Uplinks, where communications go from the ground to space, that's the biggest issue where atmospheric conditions interfere.
Yeah.
So currently, if you're sending an optical link to space, you can only do it at nighttime and where there's no cloud coverage. So none in the UK. But yes.
Okay, cool. And then I think you'd mentioned in your presentation, certainly in a chat, this idea that there might be an application in quantum computing for
Yes.
this technology. And I
Yes,
think
absolutely.
remember
Can
you
I
talked.
have the signal back on the screen?
Yeah, sure, yeah.
Thank you.
Yeah.
So this is the maser signal, and the upper peak of the signal here, and the lower peak for my quantum friends in here, these are oscillating between two states within the crystal. So this is fundamentally a superposed electron spin flips, which happens in qubits. Okay, so this is fundamentally a quantum qubit, which hopefully will be demonstrated to go over free space. So imagine quantum comms with quantum fidelity traveling over free space. That means quantum secure communication that doesn't get interrupted by space and the atmospheric conditions can give you that high security without any issue. So yes, that could be a quantum area that it can go in. But most importantly in computers, yes, a room temperature qubit is very hard to achieve. And scientists are already doing a great job going towards this. So who knows if a maser can one day be a supercomposed qubit in a computer.
Cool. So one last question here. Yeah. I didn't really pull off faking that I understood that question very well. Conrad talked about computational literacy. I think we're going to need quantum literacy as well sometime soon, because it's not just you, but basically any quantum specialist I've spoken with has been challenged in fully understanding the concept of it. But I do understand that this would potentially be a totally different branch at trying to achieve quantum computing, if I'm correct.
Yes, that's correct. So current quantum is based on individual photons or electrons flipping, called entanglement. This is based on superposition. Okay, so this is superposition of you're giving me those eyes.
No.
The superposition of microwave photons in between these two triplet states. So that basically means it's different.
Okay. Thank you. Helped dumb that down even so much that I could understand it. So.
It's okay.
One last quick question is, when I was reading your presentation, and remember you talking about the scanning possibilities
Yes.
of the maser, and I think was it about ground radar, and I thought to myself, is this something that could be scanning practical things like buildings or the human body?
Yeah, that's a great question. So radar already exists. That's radio scanning through things. And like I mentioned, the scanning your groceries with barcode scanners, that's using light and lasers. But microwaves, they can go through, like I've already said, water, leaves, and even buildings. So that means that we can potentially, where lasers are used for lightsabers, we can make a real-life tricorder, so a real-life microwave scanner that can scan buildings, find leaks in pipes without being invasive, scan the ground and find cracks in the Tyne Bridge so we don't have to close it for 4 years. All of this preventative issues, which can be made with a real-life tricorder, and we are really making it, and I'm doing it right now. So if you're excited to see, thank you.
Fabulous. Hopefully in future we can find a way to explain quantum computing in Star Trek language only. So I can understand that.
Yes, absolutely.
Yeah. Fabulous.
Thank you
so much.
Thank
Cheers.
you, everyone. There you go.